So, welcome everyone. My name is Frédéric Passeron. I'm part of the HPE Dev team, and today, along with Ellen Friedman and Ted Dunning, we'll be hosting this HPE Munch Learn number 7. The subject of today's Munch Learn is how to make data consumable for real-world data science. And Ellen and Ted will be obviously providing all the info we need about this. Before we start, a very few housekeeping items. So if you want to keep in touch with the HPE Dev team and our activities regarding Munch and Learn, we actually get a page on our developer.hpe.com website where we actually list all the different sessions that we hosted in the past and the forthcoming ones. So you have a calendar, registration links, and replay links that are available to you. The next sessions that will take place on August 25th will be around Kubernetes 101, and it will be hosted by Nigel Poulton and Didier Lally. And for September, I suppose we'll have to wait for Didier's return from his sunbathing in Spain, I would say. So we don't have the subject yet, but it will come very shortly, hopefully, on his return. Regarding Q&A, please use the chat, and I'll be making my best to actually relay the question to Ted or Ellen. And there are a few questions, a few polls within the session. Unfortunately, we won't be using Zoom polls today. So I set up a slide, and there are a few questions that Ted and Ellen are willing to ask you. So please use the chat again to answer the question. There are 4 different responses per question, either 1, 2, 3, 4. So use the number for each question to answer the poll, I would say. With that being said, I hope that you have prepared your munchie. So I don't know if we'll be able to see, but I have a wonderful tarte tropézienne for today's munch.
Oh.
So, yum, 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 yummy, 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 as we say in France. And hopefully you prepared something more healthy than I did, maybe some fruits or anything. And you can share them actually on, on our Slack channel. So you'll see that I posted a nice picture of Tux willing to eat the tropézienne, and we'll be sharing, I suppose. And so you can also tweet as well if you want on with the HPE Dev handle. With that being said, I suppose that my colleagues have shared all the necessary links in the chat. And now I would say that the floor is all yours, Ted and Ellen. Have a go.
Well, good morning. Thank you for joining us all. Fred, I'm really jealous because what I have here is a very simple cup of tea. So I don't think I came as well prepared as you did. Today, as some of you have noticed, both by our start today and some of the announcements, is we actually have a substitution for our speaker. Iveta Lepowska was going to be a co-presenter today. She had a schedule issue, and she and I will be presenting sometime later, probably in the fall, on a related topic. And Ted Dunning has stepped in. Ted Dunning is a data scientist, and he is the CTO for Data Fabric at HPE. And Ted, I think you also came without a munch this morning. Is that correct?
Well, I have a sip.
Okay.
A cup of tea as well.
And I am Ellen Friedman. I'm a principal technologist with HPE Ezmeral. Today, we are here to talk to you about how to make data consumable in real world situations. And Ted's going to share some stories, some not quite nightmare, but some of the problems that he's seen himself or others encounter, and even better, some solutions of how to approach those problems, both before and after they are problems. We are not here today to talk to you about HPE products. That said, I will somewhere along the line, see I'm wearing my nice Ezmeral color, so I'll give you a nice plug for Ezmeral Data Fabric and some other things that help with working with data, but that's not our focus today. So I think we want to jump right in. And Fred, since we're doing this slightly differently, let's actually start, even before I start the slides, let's start with our first poll question, if that will be okay, and let's see how that works. And so audience, we want to start off and ask you just roughly, how would you characterize your own level of expertise with data science? And please respond in the chat.
Can you see my screen or not?
Yes, I see it. And yeah, just question number one at this time.
Yeah, so just question number one, what's your level of expertise with data science? If you put your response in the chat window, just numerically, number one, if you feel you really don't have experience with data science. Number two, you're only starting out. Number three, you own your own data lake, you're regularly in it. And number four, you dive in regularly. And I guess I'll have to add, you dive in and you can actually climb out again. So that's your level 4 expertise. And we'll just take a moment or two for people to enter their solutions or their
responses. And I have to say, yowza, there's a lot of responses coming in.
Yeah.
Pretty cool.
Well, there's a majority of 2, I would say, and a few 4, actually, and some 3, but I would say the vast majority is 2 so far.
I do notice, though, the people who answered late are the ones.
Yeah, indeed. Yeah.
I don't know what that means. I have to do some. I love the way some people are saying that they're 2 and 3.
2 to 3.
Yeah.
Oh, I like that. Yeah. The ones I would worry about are the ones that answer that they're 1 and 4.
Yes. Yeah. Well, I'm sure there are some people who are both none and they dive into it all the time. That's part of what we're talking about today, in fact.
Yeah, it's a vast majority of 2 moving to 3, hopefully after the end of the talk.
Oh, that's right. That's right. All right.
Okay.
Shall we say, enter your last responses, and we'll go ahead and close this and move into the talk as I figure out how to share my screen and get to the slides.
Okay,
so
I'll stop sharing then.
Moment of technical weirdness while I do that. So Fred, I'm taking over the screen from you. Is that okay?
That's good, Ellen.
And there we go. And do you now see my slides?
Yeah, and you can start the presentation. Yeah, there we
go.
Great.
A little more rearrangement here. Well, I think I can't move that out of the way. All right, so as I said, today we're talking about how to make data consumable in real world situations. This is our contact information, and we'll repeat this at the end of the talk. Both Ted and I would love to hear from you during the talk. Please put your comments in the chat window. After the talk, feel free to reach out to us and follow up with your ideas or comments or questions about the presentation today, or indeed reach out to me, or I think Fred or other people, if you have ideas for other presentations you'd like to see, other topics during this Munch and Learn talk series. So let's jump right in. What happens here? And when you go to fix your bicycle, and I'm going to ask, I keep having a menu that falls down and covers part of the slide. Do you see that as well?
Just keep going, Ellen.
All righty, here we go. So when you go to fix your bicycle, have you ever had something like this happen? You pick a good, reliable, and simple tool like this screwdriver on the left. You go to your bicycle, and what happens is that you find that you have a mismatch. You have a problem, a mismatch between the tool and, in this case, the screwdriver and the screw. It's not a matter that either of them is defective. It's simply that they don't play well together, and that as you go to do something in the real world, you may run into surprises, especially in things that you haven't completely thought out ahead of time or explored or investigated. Now, this is just an analogy for some of the things that happen in the real world as people work with data and work with data science. Ted, you mentioned to me an example that popped to mind when I said this to you about people working, I think, on a Norwegian, was it an oil and gas drilling platform? They ran into a data problem.
Yeah, actually, they were using the hexagonal screws, and I brought a screwdriver. And what happened, it was an interesting problem, one we never thought about. they had been for years collecting data. The purpose of the data originally was for monitoring. And so they needed the last 10 minutes or last hour of data for the monitoring graphs. And so that's the way they collected it. And the monitoring was all done locally. And so that monitoring involved recording the data as well. And the data was recorded with the time, just as the monitoring application would do. But when they sent it to us, the purpose was for predictive maintenance. Unfortunately, they had not bothered to store the location, nor had they stored the date on the data. They only stored the time because that was perfectly good for the monitoring application. So we had to jump through some real hoops to figure out what the location was. That was from the file name that we figured that out, and figure out the date. Well, we were able to do that, estimate that by passage of time and successive days in order. But if the data had been reordered, we wouldn't have been able to reverse engineer that. And that's an example of just this incompatibility of purpose. My purpose with the screwdriver was different from their purpose with the hex nuts.
So these are really just examples about the fact that data, of course, data science is all about the data, but the question is, how do you make that data consumable, practical in real world situations? And you will, in all cases, have things that you need to do to work with data, to clean it up, to make it consumable. But in some cases, you run into things that are real challenges. And some of those are because the person who is consuming, the data scientist, is using that data may not be the person who collected it. Because, as an example, many times data is being collected for one particular purpose, and then a data scientist comes in and wants to use it for a different purpose. And so the way the data is collected, the way it's labeled, may not be a direct and good match for the purpose the data scientist is using it for. I mean, something as simple as people collecting metrics or machine data in a big industrial setting locally, as Ted described, may have no reason to actually mark the location of that machine or setting or where that sensor is located, because they are only looking at one site. That's why they're collecting the data. But people later want to look at an aggregate. Maybe they're doing predictive maintenance. They want to look at an aggregate of data coming in from a number of different locations. And in that case, they actually do need that location data added. And so in all of these situations and all of the challenges that we're going to talk about, and I'll keep challenging Ted to say, but what can you do about it? And sometimes what you can do about it is simply think about it ahead of time, explore it, find out that your screwdriver may not match your screw. Maybe there's a simple solution then, or maybe the answer is there's missing data. There's a situation where this just isn't going to work. I mean, be aware of that from the beginning. You're going to have to look for a different solution or different data. In some cases, for example, with missing data, there are techniques to be able to interpolate and so forth. So we're going to look at what you can do in each of these situations. And we're just going to pick some as an example today. And some of the ones that we'll be talking about are the challenges that you see with time data being mismatched, collected for a different time period. Maybe, again, with the machine, you may be looking at it for a very short time period, and later people want to look at a history over a longer period of time, and they need to be able to adjust the window. Or time is recorded in different time zones and not recorded in a consistent way. Maybe people didn't record time at all. Same thing with location data. Again, sometimes it is recorded, sometimes it's not, or it's recorded in a non-standard way. It may be labeled by the name of a plant or a location instead of some sort of universal or standard way to refer to locations, such as latitude and longitude, where you can easily combine data coming from different sets. And there are a number of other situations in which you'll find that data is missing, or that annotation and labeling and metadata to indicate how the data was collected is what's missing. Ted will also talk to you a little bit about the challenges of what he's calling quasi-text. And there can be mismatch, especially when you combine diverse data sets. This is an increasing trend. There are just some beautiful new initiatives out there. One from HPE called Data Spaces. There's an open source initiative from the Linux Foundation called AgStack. A number of others where people are making large data sets available for multiple different projects by outside data scientists. But how do you combine those? They're data collected in different ways for different purposes. And often the issue of mismatch is just one of granularity. Maybe you're trying to look at data for a particular small geographic region. Maybe the data is collected or organized across a larger granularity. And there are some tricks to go in to adjust and fix that data and make it really consumable. So let's dive right in. These are the examples that Ted is going to be talking about today. And he'll start with measurements at non-aligned times.
Yeah, and there's been some nice activity in the chat window, by the way, talking about exactly what, asking in some sense, exactly what we're talking about here today. Also, Ellen, commenting about your bicycle. Some people were surprised that Americans rode bicycles at all. They thought we only drove cars. Can you start the presentation again?
Yeah.
So anyway, the point of what we're talking about today is how we make use of data that is somehow intended for some other purpose. And this issue of non-aligned times comes up a lot in this reuse of data sort of situations. In particular, when we're measuring from machines, either real machines in the real world that are making things or in a factory or something like that. Often you want or cannot avoid having sensors measure at the moment that they need to measure it. So for instance, you often have a microcontroller that's connected to 20 sensors and it measures one at each time. And so all the sensors come in at different times. Often you also want, especially when you're measuring from computers and you're getting an enormous number of these measurements, you want the measurements to come in not time aligned because you don't want a million measurements exactly at the same second. You want the data to be spread out a little bit. But the fact is, these non-aligned times are a very common issue. Let's go to the next slide. So here are three synthetic toy-sized data sets. I've labeled them as red, green, and blue. Normally, I would pick better colors and change the shapes. I hope everybody can see this today. And the point here is that we have times on the left and values on the right. And we would like to just say, well, what's the average value or something like that in order to use that as a feature for, say, a machine learning or a dashboard system. So let's go to the next slide. And if we plot those things, time on the horizontal axis, value on the vertical axis, none of those times actually align. In fact, the intervals don't even align. There's long intervals where we don't have some measurement. Next slide shows exactly how these times come down. And if you try to combine them, say with SQL, it's very common that people will try to group by time and average the values, and they'll get something like this in the next slide. They'll get an average value, which is just the original data points, because there will be exactly one data point per time value, and therefore that will be the average. Laurent in the chat asks about time zone, and I'm only addressing this one question. Time zone is a huge problem. Please, nobody ever use anything but a universal time zone if you could possibly do that. But I've had data that was in different time zones. I've had data that was labeled with wrong time zones. These are all forms of broken data. Sometimes you can re-estimate the actual values. But in this particular example, where we have these time series with restated things, often what we want to do is shown in the next slide, which is to interpolate Can we go to the next slide, Ellen?
Trying.
There we go. Good. What we want to do is interpolate with each data set individually to whatever data timestamps that we want, sometimes regularly spaced, sometimes at every sample point that we have. And then we can do the averaging that we're talking about based on the interpolated values. Or we can do what we show in the next slide, which is something more advanced, which is a low S smoothing, which uses several neighboring data points to show, to generate a smoothed value. It's also using data that's not showing off to the right of the graph. That's why it's getting a little surprising bit of an average there. But the point is that we need to rectify, literally rectify, to reduce to a common time standard in order to make sense of these data. And this applies as well to data that's geospatial, which it also has a continuous independent variable there, two-dimensional variable, in that case, latitude and longitude usually, where we have the same problem that measurements are at individual points, but we often need to talk about them in the same frame of reference. Sometimes measurements will even refer to areas or periods of time, which are areas in time, obviously. And we need to somehow deal with non-overlapping or non-equivalent areas. And this sort of interpolation comes up in those issues. When we get Iveta back, she'll deal with a particular health care related example where she had to deal with just that. If we move to the next slide, here's another problem that you have, or an opportunity, you might even say, that you have in geospatial data. And we see this in the real world in California, all along the West Coast recently, in terms of air quality. You have a few sensors in this example that have low frequency measurements. These are the stars, but very good calibration, very good resolution at small data values. And these are the sensors that we would like to use because we know their accuracies and things like that. But because they only report every few hours, and because they are geographically spaced far apart, they're not as useful. On the other hand, we might have a large number of consumer grade sensors. This might be due to mobile devices, or in the case of air quality, there's a company that sells these devices, and people then can report their data onto the internet back through that company's website. And so you have this army of data sensors that report very often. They have very high data frequency, but they are not calibrated at the same level as the laboratory quality standards that the government's running. And the cool thing we can do is we can derive calibration for the low-cost sensors that are near the high-quality sensors. Take a step, Ellen. And we can represent that by these things turning green. And step by step, the newly calibrated values can help us calibrate other values, or we can use device characteristics if we know there's consistency to calibrate ultimately the entire data set. And so what we get there is high frequency, relatively high quality data. If you live in a neighborhood like mine, which is on the left here of this graph, you have this is synthetic data, so I don't have to worry about whose data I'm showing. The density of nerds in my neighborhood is very, very high. And so the density of these home deployed sensors is also very, very high. We can get air quality resolutions at roughly 100 meter resolution and 15-minute time resolution. It's really fabulous when you're trying to figure out, is there a fire coming our way? But
Ted, I'm just going to jump in and say, again, connecting this back to real world, and this is well, not quite a toy example, but a small example, but a really excellent one for any of us on the West Coast who've lived through fire and smoke recently. We kind of live by looking at these air sensors, but it illustrates a number of things that you've just pointed out, and I'm just going to say it back to you. One is individuals here are collecting that data for their own purpose, and they wouldn't need to mark a location because they have the sensor in their backyard. They know, they go look at it, they know where it's marking. But to look at it collectively, obviously you have to know the location. Yes. Secondly, there's the time sense of it. If you just walk out and look at a sensor or do your reading in your house to say, right now, what's the air quality? Can I step outside? That's fine. But if you want to be able to track this over time and look at trends, such as a smoke cloud coming, you definitely have to have that continuous data. You have to know the timestamp. You have to have it in some kind of a consumable way from one sensor to another. And then you've talked about also the relative accuracy of these sort of at people's home sensors relative to the more accurately calibrated ones, but ones that are taking where you have less granularity in terms of the readings.
Yeah, and this applies in all kinds of settings. It isn't just these particular air quality sensors, because what happens is very often in say a factory, if you can pepper all of the machines in a factory, all of the machines or process steps in a continuous process system, if you can just absolutely pepper the place with sensors, you can get very, very high spatial resolution. You can get lots of oversampling of the data that you get. And that then enables you to detect things like failing sensors much more reasonably, because if something is out of whack with its neighbors, you can see it. Whereas if you have only a few sensors reporting on a lower time scale, perhaps with higher quality, you can't necessarily distinguish a sensor failure from a process failure. So this is actually an opportunity. It also illustrates, by the way, some nice aspects of how you can build in data quality. These sensors that are being put out, and frankly, we're working with manufacturers of sensors in a larger sense to help with this as well. They automagically put in the time when they report the data. They also, by design, put in the location as accurately as they can determine it. And that means that the data is useful right off the bat, even beyond the simple use, which is go look at my dashboard on my phone for my air quality at my house. I may not care about history. I may not care about other sensors when I ask that one question, is my air filter making the air quality in my house better?
So,
but other times,
Ted,
I really do.
Just as a time point, we're at about half of our time. I think you have some additional examples.
Let's work to the next example.
Okay.
That was really kind of like 5 examples all wrapped up in one.
Yeah, absolutely.
Yeah. Now, when we deal with the same kind of data, and this actually begins to verge into transactional data as well, because we get this sort of thing, we often have data that has variable availability. So if I were to take an IP address that's similar to my home address, it's not exactly, I don't know whose actual IP address this is. On the next slide, I did a geolocation of this IP address. And indeed, since it's a perturbation of my own address similar to it, it came up as being roughly in the same location. Now, the geolocation takes me back to a region, but the latitude and longitude are reported as the center of that region. In the next slide, I do a different address. Now, this happens to be the DNS server for Google. It's not a particularly interesting address to DNS locate, but spammers often try to obfuscate their geolocation, so they wind up with results very much like this. Here, the city and the state value are missing, the country is valid. And so the latitude and longitude that are reported are the rough geographic center of the US. And if we draw a map, that happens to fall in the middle of Kansas. Next slide. Bingo. Now, previously, in fact, those values were rounded in a particular way. And this landed right in somebody's front yard. And that was disastrous for their life.
So Ted, you're saying there wasn't an intention to locate this in somebody's front yard. It was by obfuscating data, that missing data and so forth, that
was being
puts
handled
it here.
Poorly. Instead of attributing it to the polygon that is the United States, attributed it to an individual point.
Bad news for that person, I would think.
Yeah, and that's the next slide has a link to an article on the topic. 600 million devices were mapped to that person's front yard. And so people started showing up saying, you are the spammer who's been sending me stuff. You are the denial of service attack point, and so on. And the moral here is that the missing data was being handled reasonably well down the chain, but when people looked at just the final result, latitude and longitude that they wanted, they didn't notice that latitude and longitude was exactly the value it had because certain data were missing.
So what should people do? What do you do about a situation like that?
Yeah, the way that you can handle this is you can do simple counts. It happened that 600 million devices were at that location, and that is itself the indicator that something is wrong, that no location has anywhere near that many, within a factor of nearly 1 million, that many devices in exactly the same location. And so that's an anomaly right there. And often the way I've dealt with this actually is to use a feature which references simply the number, the frequency of a particular value. Rather than looking at the actual semantics of the value, the simple frequency of it gives you information. And that can often detect weird missing data effects like this. So I've seen in banking systems, for instance, where missing data originally was kind of Y2K affected. It had 2-digit years. And so they used one convention for missing data. Then they went to 4-digit years and they use a different convention for missing data. So there's multiple kinds of missing data. And the simple frequency of that thing tells me which kind of missing data it is. And that then can often tell me indirect effects like the age of the account, which is very, very interesting from the standpoint of fraud detection. This geolocation also tells me interesting things. When I get this non-committal location, but it's supposed to be an actual mobile phone, I know that something is up. So you may not be able to reinsert the missing data. You may not even be able to detect that it is actually missing data because the data you're looking at looks well-formed and complete. But by indirect means, like the frequency of the exact value that you're getting, you can often determine that the value is somehow an anomalous measurement.
So the overall lessons here for people are, first of all, think in context, think about how you're labeling data, how you're collecting it, and the implications. Examine and explore, like you said, look for anomalies such as 600 million pieces devices mapping to one spot. Maybe that spot isn't being listed in the way you intended for it to. Use the methods that you've mentioned for interpolation and so forth, and in general develop a practice that you are collecting and marking data, annotating data for your own purpose at the moment, but keep in mind that it may be of value to others. Indeed, it may be of value to you in some other situation. And so develop good standards of practice, best practice for how you collect the data and how you annotate it, and try to do that in consumable and standardized ways. Does that make sense?
Yes, absolutely. And Peter had a very good comment in the chat just now. It says, if we have millions of records, can you build a model to detect missing data? And the answer is, the classic computer science answer is, it depends. Sometimes you can. Sometimes the best thing to do is not necessarily build a model for missing, which you may or may not fully understand, but build a model for weird. And this counts as that sort of thing. And it's important to stop.
So a model for weird is another way of saying build an adaptive model that does basically outlier or anomaly detection, so that you have an adaptive baseline. You're not defining what's normal, and your model is then not only defining normal for you by observation, but it's also noticing when things are very far away from normal.
Yeah, and I had exactly this kind of thing happen once when I was trying to build an identity fraud model. We came up with 15,000 young adults who seemed to live in a rural location in Pennsylvania. It's like, whoa, clearly that's identity fraud going on. But when we looked at it, that address was associated with very low levels of identity fraud. What it was is that was the headquarters of the Watchtower organization, and that was the address that they had their missionaries use while they were out on mission, when they would not have stable addresses. And because those missionaries were under kind of close social observation by their peers, the fraud rate among them was actually very, very low. It was hard to steal their identity because they were kind of new, but they also had a very insulated lifestyle, and they themselves were not involved in fraud. And so, again, we had exactly this kind of problem due to a very, very different kind of mechanism. Who would know that we would wind up detecting missionary activity when we were looking for fraud?
So I think that we have time for another example. Did you have another one you wanted to show?
Let's flip through. And these examples will get shorter and simpler. And this is first an example which illustrates that I'm always uncertain how do you spell the word pseudo. But the idea is that in data, you often have what looks like garbage. Often people refer to it like the junk DNA of data. The first one is roughly what a merchant ID in a memo field in a credit card transaction from a bank might look. The second one is something very, very similar to the way that we used to see data about music being annotated by people. And the last one is a part name, which has completely free format. And the issue here is that these are not controlled formats. The first one is an interaction between the point of sale terminal and the bank that's clearing the transaction. Things are changing all the time. You have tens of thousands of banks. You have hundreds of thousands, if not probably millions, of point of sale terminals. And so it's just kind of texty goo that's coming out there. The second one, all the people in the world have their own preferences about how they talk about their own music. And so they change stuff. And the last one, you have, again, multiple automated systems that are kind of gluing data together from different systems. So you get kind of understandable goo. And the answers are on the next slide. The way that you can handle these, I've used multiple techniques for these. And often I found the most information available for me, the most new information in these pseudo text fields, especially in fraud detection, because these fields have rarely been used traditionally. And that means that the fraudsters have very few countermeasures built around the data in these fields. They're not aware that we're getting that back channel information, and so they haven't taken any actions to avoid us. In music, there's only a certain number of only a few pieces of music that exist, only what, 12 million that have been published. And with very close matches, you can just make the match. With slightly less close matches, you can just manually encode it. And because there's not that much new music any given day, the manual encoding works pretty well. It's a static world. For noisy things like vendor names and parts, you can actually use systems like BERT, which is a transformer network, a neural network technique on short groups of strings, like the 3 or 4 letter sequences in there. You don't even have to depend on words being separable as words. And you can build vector encodings that go letter by letter. And you can derive semantics from that. And you can use a deep neural classifier to mark things this way so that you would detect, for instance, a money laundering location, or how all the different ways a particular kind of money laundering situation appears in your data. For a more clean thing like stack traces, where these are generated automatically by a single system, you can use normal word segmenters, space and punctuation separated words, and you can use a log likelihood ratio test like the G-squared test. Ping me afterwards if you want more detail. You can find then interesting things. So you could compare all of the crashes with all of the stack traces you have from normal operations, and that will pop out the code that appears to be offending and causing the crash. You can do this for IO operations. I've done it for previous merchants to detect common point of compromise. And all of these things give us a lot of value out of pseudo text. And it really depends on where that data is coming from as to how you use it.
So let's move on.
Let's move up.
Yeah,
let's move back to you, Ellen, for more of the less the machine and more the human side of this topic.
Well, and before we do that, we're running a bit late, but let's take time for the another poll question. Let's see. There we go. Let's do these last 2 questions. We'll start with question number 2, and would like to know, what types of data do you usually work with? Please respond in the chat window with the number 1 if you mostly use transactional data. Number 2, if you look mainly at machine data, machine metrics, or sensor data. Number 3, if you work with entirely different classes of data. And number 4, if you don't primarily work with data.
I'm seeing a pattern that there's not a lot of overlap. People use, there was one person who said video. People tend to do the machine sort of stuff, maybe others, the sensor sort of things, or they do transactional data. And I've definitely seen that split in my history, where sometimes we use one of those and sometimes the other. Laurent says he uses CSV and text, which can be very messy to use. And Stephen uses a lot of text. Well, that's very cool, very interesting.
So here I've been advising people with their data so that they don't have ugly surprises, that at the beginning of a project to go and explore, find out what's really there. Is the data what you think? Is there a mismatch? And I think there's a lesson to self, is that you should really examine things carefully, including whether you plugged in both ends of the cord for the power for your laptop at the beginning of the presentation, or if it's just not plugged into the wall and you get a little message like I just did that the battery's about to go. And actually, carefully checking that it's plugged in here at the computer. So
I've seen that done in the field by professional people installing hardware.
That's it.
Yeah,
so
it doesn't work as well that way. So,
all right,
let's move on.
And let's go ahead with that 3rd question, just as we're short on time. And I'm about to get into things related to this. So question number 3 is, does your organization have formal procedures for annotating data and recording metadata? And in other words, not just do you do it, but is there kind of a standard method, a formal method for making sure that it's being done in a consumable way? So give us a number 1 for yes, I don't know how to make this thing not overlap, so I can't see the answers, but number 2 is yes, your organization has a formal procedure, but it's not consistently executed. Give us a 3 if you do some sort of annotation procedures, but they're informal. There's no organizational wide formal procedure, or if you don't really have procedures like that.
And the lesson that I'm seeing out of this is kind of depressing, but kind of as expected. Almost nobody is answering 1. This is a little bit like putting comments in code. People often have answers that they had. And I'm actually seeing some people from the same company answer both 2 and, did we have standards? So that's the classic sort of situation there as well.
And so I'm going to tease you with this. What does the term plant engineer mean? What we're going to talk about now is that there's a human side to all of this, the challenges of making data consumable. And the human side has to do with finding the right context, having the right communication. And these are not just kind of touchy-feely, soft terms. It really can make the whole difference in defining the scope of a project correctly, of making sure that the data scientist does actually understand what the data represents. They weren't the ones that collected it. If they actually understand what the annotation around the data means and what the intention of the question is. So I've put this as a reminder to myself. This just happened during HPE Discover and some of the prep for that. I was on a panel with the data scientist, Dr. Suparna Bhattacharya, and she was talking about using agricultural data and data science. And then at one point she said something about a plant engineer. And I sort of perked up because I used to have a background in molecular biology, and I did plant genetic engineering. And I thought, oh, great, she's about to talk about that field. And of course, she meant plant engineer as in the more obvious thing, an engineer in a factory or a plant or a production agency. So there could be...
I want to interject, Ellen. The people who answered 2 in the previous thing, who did sensor data, they all thought it was the factory meaning.
Yes. And so, like the screwdriver and the screw that mismatch, these are simply things that are in some way in a different context. And you can imagine that the communication between a data scientist and a non-data scientist, somebody with different domain expert, even different data scientists working on slightly different aspects of a project, and even if they all, in theory, speak the same language, there are just these barriers to communication. And it's not just the communication barrier of technical jargon versus not, although that's an important thing too. And so these really do have to be dealt with in a very serious way, or you come up with tremendous problems in what you do. And so the first suggestion that I have for doing this is to adopt formal best practice procedures across your organization, whatever that means within your organization, but don't just go at it by saying, I'll exercise more and get in shape. Actually make a plan and have a formal procedure for it, because otherwise it doesn't tend to happen. This little reminder here, and you might later want to look at this this video, is for example, people in transportation. This is in train safety. They have the engineer actually do what's called pointing and calling. They point at what they are supposed to observe. They reach over again and formally point at a checklist. They don't just assume that they looked at it. They have to have a formal procedure for that, both to remind themselves and to be able to record it for others. When an airplane arrives, you hear an announcement of disarm the doors and do a cross-check. It's not just anybody decides, oh, I think we've landed, I'll make the door ready to open now. There are serious reasons for having this as a formal procedure. And this applies to what you do with your data practices as well. So these are just some practical tips. We don't have enough time to go into them in detail, but I'm just going to run through them real fast and just touch on them so you can think about how to make a difference in how you do this communication. My first suggestion is say back what you think you heard. That sounds so simple, but it can make a tremendous difference. when you are setting up a project, when you're talking to somebody about how data was collected or what the question is they're asking, what's going on, hear what they're saying, listen to it, but then say back to them, this is what I think you just told me, and make that a formal and expected cross-check in your procedure. Because right there, if there was a mismatch in the understanding, it'll pop out before you've wasted a lot of time, doing work that didn't make sense because you didn't actually understand what the label on the data meant. Related to that is clarified terminology. For example, when people doing fraud detection, there may be very strict or legal sense of what is formally labeled as fraud. Here's transactions that represent fraud. But experts also have much larger amounts of data that they've examined that have the shape and the pattern of typical fraud behaviors, and which can be very useful to use in a model, even if they haven't been formally identified as fraud. By translation, again, I mean, people with different background, different context talking across that hear things slightly differently. And so just realize that that translation has to be in there and make time for it, make an effort for it. Again, I was using an example of credit card fraud, but when a domain expert, a person who understands their business and the transactions, says gas station, as in we see transactions where somebody does a charge at a gas station, the data scientist thinks merchant type, and that's a whole category that they might use in a fraud table. And when the domain expert says just before, meaning a fraudster does a transaction, small transaction just before they try the really big fraudulent transaction, the data scientist must think of that in slightly more formal terms of exactly what's the time period, or do we want to look across several time periods? And so these are just habits of communication, but to make sure that each group understands what the other one's saying. This becomes easier to do in your organization if you have a data ops style approach. And by that, I mean, for people with data skills and working in data science, and people working in data engineering, people with domain expertise. In other words, you build teams that are cross-skill teams. And those teams see themselves as being in the same boat, pulling on the oars toward the same goal. So they are part of the same project, and therefore they see themselves with those shared goals. It makes communication easier. They don't feel like if you're asking them a question that you're intruding on their work. You are part of their work. And that really makes doing these other suggestions for communication more effective, and people have more experience with it. And the final suggestion I have, we've alluded to this throughout the talk, but develop formal practices for how you're going to annotate data. Do that across your organization. Use it, do it. But mainly, as you think about annotating data, think about the fact that that data may be used for the purpose that you currently have in mind. It may be used by others for very different purposes. As we said, the difference in collecting data for some local analysis versus later a data science project is doing some aggregate analysis. You're going back and looking at longer term histories. And keep in mind that that business of thinking you're going to annotate it in a way that it can be understood by others, the other may actually be yourself, your future self, going back to use data at a later time. You need to understand exactly how it was collected, even if your new use for it is different than your original one. So these kinds of practices can actually avoid some of the problems of that you run into in trying to make data consumable by just basically setting it up in a way to make it easier to use from the beginning.
And Ellen, I'd like to point out that some of these data issues have been where I felt very clever in my career, whereas these human miscommunication issues are where I have the most embarrassing stories. So yeah. I would put a high priority on those.
Great. So thank you all. I'm sorry we ran a little late. We have, I think, 5 minutes left in the hour, and Fred has a little bit of some closing things to do for us, but we do have a few minutes to take just a few questions off the chat if there are some. I'm showing you as we do that, this last slide, which just suggests some other resources you might go to dig further into this business of how to work with data. And let me stop sharing my, well, I'll keep sharing. Ted, do you want to start looking at some of the questions in the chat?
I've been doing that consistently as we were going along. And
Great.
So much right now, what we're getting is people saying nice things with exclamation marks.
Well, that's awfully nice. So I'm just going to summarize with this. The lesson here is to, yes, and there are these final poll questions. But as you do that, I'll just say the lesson here is that, oh, and thank you all. Thank you for these responses and thank you for participating. I think the final lesson here is to recognize that data in the real world is not a clean, simple data set like it might be in a machine learning class. You're going to run into problems. Plan for that. Leave time for it. Budget time for that part of the data prep and data analysis and data exploration. Build good conversations around that. Go to domain experts. And domain experts include business people who understand their own business, as well as people with much more technical information in different fields. Constantly question what your data actually is. Does it represent what you think it does? Are there missing pieces? And then use these different techniques that Ted's gone through for dealing with those problems when they show up. Again, budget time for doing that, because that will happen in almost any project. And that way it moves you forward and keeps you within your reasonable time frame for doing this.
And
so
Ellen,
I think that's all I had today.
Could you go to
Fred?
the context slide? I think
Say again?
Isn't there a final how to contact us slide?
Yes. Let me see if I can.
There are 5% of the people who said this wasn't technical enough. And to those 5% people, I would love to hear from you. We have a lot of technical backup on these topics. And if you reach out directly to me, doesn't the next slide have our contact info, Ellen?
Yeah, I was just letting the polling finish.
Okay.
And I think it'll let me advance the slide.
Yeah,
there
it just did. Yeah. So reach out directly to us and we'll be happy to give more technical, a little bit more technical, or a lot more technical resources on these topics and dozens more. You heard Ellen trying to accelerate me through this. There's way too much to talk about in just an hour. And so let's make this be an ongoing conversation. So go ahead and reach out. Both of us have nice, easy emails, ted.dunning or ellen.friedman@hpe.com.
And for the deeply technical questions, that's really for Ted, although I'm happy to pass them along. He's the one that's really built these systems and has the deep experience with it. Fred, I think you have some closing remarks about what's
well, I would
next.
say that if people are looking for more technical, type of information, maybe we should discuss with Ted and you about a dev talk, which could also be an interesting format for internal talk and more technical talk. So that's something
that would be great.
We should discuss further. With that being said, I mean, we have the final slide. I mean, the HPE Dev community website is the place where you'll find everything about our community, being the blogs, being the platform, being the workshops on demand, and so on and so forth. And with that being said, I would say a big thank you to you, Ellen, and you, Ted. That was a really interesting session, and I'm pretty sure that the comments in the chat are just overwhelming, and they are just assuming that you did really, really well once again, as usual. And I was not surprised, I would say. So thanks again for your time. This was a really interesting session. And go ahead.
Fred, we have one good question just popped in. Do this as a poll. Can people suggest other topics that they would like to see? If you could put that in the chat right now, and if not, then reach out to us directly.
Yeah, you can use the chat, and we'll check them. Or can send an email to us, frederic.passeron@hpe.com, for instance, myself, or Didier Lally, that I saw joining the call, whether he was still in Spain, he's still doing the call. He was really interested as well. So you can join Didier as well, didier.lally@hpe.com. And if you're coming along with some new subject that you would like to be covered in the Dev Talks or Munch and Learn, we'll be very, very happy to learn about it and to propose them and program them along with some speakers. So with that being said, I finished all my munchie. I hope you did as well. It was really good while listening to you, obviously. And well, talk to you soon and have a very, very good end of your day. And the next session will be held on the 25th of August, and it will be Cube 101 with Didier and Nigel Poulton, Kubernetes 101. With that being said, bye-bye, everyone. Take care.
Thank you.